As well, from me, welcome to the session and the PCB track. And as mentioned, I would like to give you an idea how to implement and how to analyze complex SerDes links, as mentioned, as USB or PCI Express using CR-8000. So I structured the presentation as follows. That I would like to start you with a little bit of motivation. What is the motivation that we have ever and ever faster communication links come into existence? I would like to introduce just briefly what's the idea behind SerDes, which stands for serializer deserializer technology. And I would like as well to explain briefly what are the special kind of signal-integrity problems which SerDes links are exposed in names, jitter, loss, bit error rates. I will explain the technology underneath. Most of it is based on LVDS. However, it is a kind of very advanced and fascinating technology. It is per definition a kind of multi-board problem because these SerDes links typically connect different systems together, like your USB cable or any kind of PCI Express links. They are connecting several boards together. I would like to explain what is the challenge in defining all the necessary rules, in modern words, constraints for the PCB design process. This involves the definition of the basic PCB technology, so the layer stack and beyond. Then we have the implementation itself. We have the placement with the routing. We have mainly differential pairs, which have requirements on symmetry, on skew, on loss, on eye opening, on bit error rates. And this leads to the analysis tasks, which are defined by SerDes links, which I would like to introduce as well, how they can be addressed using CR-8000, how you can gain in a fast and easy manner eye diagrams and bit error rate figures. And then I would like to end with explaining the models underneath, which are so-called IBIS AMI models and S parameters, and then to end with a brief summary and conclusion. So that's our schedule for this afternoon session and the PCB track. And on the right-hand side, we have a few examples what's comprising SerDes links. I'm sure that every one of you is using them. Probably you're not aware of that, as we have all the different technologies like HDMI, like USB. That's all having SerDes underneath as basic technology. So I'm speaking on SerDes in the next 35 to 40 minutes. As mentioned, SerDes is the abbreviation for serializer deserializer. That's a technique which will transfer a parallel data stream into a serial data stream. So the older of us may remember the old Centronics printer interface. That was a parallel data interface. Meanwhile, we have more or less only serial data interfaces on our boards. This has many reasons. Cost is one of them. Space, board real estate, form factor is the other one. And the main reason that we have this transformation from parallel interface to serial interface is bandwidth, means how fast you can transmit data in an accurate manner. And we have this SerDes, as mentioned, everywhere. It's not a new technology. Keep in mind how old USB is these days. And USB is the SerDes links. And some of these SerDes links are commodity. You use HDMI very likely on a daily business. We have PCI Express everywhere. We have DisplayPort. We have SATA connecting our hard disk and our computers. So we have SerDes everywhere, but most of it is somehow under the water. But it's defining serious design requirements, and it's getting momentum. Because we have meanwhile SerDes chips, so-called SerDes PHYs or SerDes transceivers, which are available for a few pounds sterling, up to 10 pounds or even less. So automotive is diving into SerDes, and they are doing that because they have to handle huge amount of data. If you think about autonomous driving cars, an autonomous driving car has to know where it is, has to know where other cars are, and has to know where obstacles are, like any kind of people running across the street. So this data has to be collected, this data has to be computed, and this has to take place pretty fast. So SerDes is not a niche kind of application, so it's not nerdy. It's becoming a technology which is widely used. It is somehow complicated because it's sophisticated. However, it can be managed, and I would like to introduce how it can be managed using CR-8000. One of the characteristics or one of the figure of merits for SerDes channel is an eye diagram like the two which are depicted on the right side of that slide. So that's one way to characterize SerDes channels. But let's step a little bit back and let's have a look how human beings do communicate. Because what's the driving factor? The driving factor is bandwidth of communication. So in the very old time, we had different communication techniques. But these days, just transmitting data from A to B is required but not sufficient any longer. The fancy thing of SerDes chips is that you can tune them. Means by setting information into a register, you can define or change its performance. You can change the output voltage swing, you can change the energy which the buffer is feeding into the channel. So you have different parameters which will influence the transmission behavior, and that's making SerDes that unique. So I like to give you just an introduction because it is a very technical feature, but I can promise you, I think this one is the only formula I have included into my presentation. The SerDes development is driven a lot by the IC vendors. So they have implemented very sophisticated pieces of silicon. The information technology has changed over the last couple of years. We had in the digital areas the transport of an information just by the changing state from a 0 to 1 or 1 to 0. So we have 2 states. Meanwhile, we have very often 4 states. So we have a thing called pulse amplitude modulation for 4 different states for carrying an information. Modern technologies are moving to PAM8. So this allows to implement SerDes links up to 224 gigabit per second. To compare this with a PCI Express GAN 4, so that's typically 8 gigabit per second. So we have here a revolution in the bandwidth, and that's driven by IC vendors, but as well by signal integrity vendors. So this will involve different kind of analysis problems. This is still under the umbrella of signal integrity with its buzzwords, impedance, reflection, crosstalk, ringing. But we have now new kind of problems. We have loss, we have eye openings, we have bit error rates, which make the whole thing that complicated. And this is one of the reasons that virtual prototyping these days is paramount to finish such complex hardware engineering projects in time with successful time to market, time to volume, time to yield. Just a remark before I go to the further details. Typically, SerDes link modeling is involving to tackle S parameters. S parameters are a methodology to describe passive interconnects in the frequency domain. So, how human beings do exchange information and what is the impact or what is the meaning of bandwidth and speed. More than 2,000 years ago, we had communication schemes very limited. So one example which is known in literature is that you had a fire signaling scheme, which is typically operated by slaves, and the capacity, the bandwidth, is limited by the speed the slave can raise his arm up and down. Then we had a little bit of evolution. We had other communication schemes like pigeons with small letters in the small boxes as well, limited in bandwidth by the size of the box. and by the speed of the pigeon, and we had a kind of a failure rate because some of the pigeons never arrived at the destination. We had then 200 years ago different, a little bit more modern signaling schemes, like to transmit information from ships to ships, driven by marine applications, or we had a signaling scheme in place in Germany between Berlin and Koblenz, which has been able to transmit a telegram within 20 minutes from Berlin to Koblenz, but limited bandwidth, but speed is increasing. We had other things 150 years ago, which we know from the Western movies from Hollywood, like Stagecoach, Pony Express, and then electricity arrived into the game. So we had the Morse telegraph. And this was a kind of a game changer for both for speed and for bandwidth. However, bandwidth was still limited. 50, 60 years later, we had teleprinters, we had telex. Some of us may remember old telefax machines. And then we had the invention of the internet. We had email. Now we have internet, we have Wi-Fi, we have Bluetooth. 20 years ago, I had my first business trip to Japan. Even these days, we had kids in the subway working with the phones. This is now a commodity everywhere and not limited to kids anymore. Regardless where you are, the people are connected to the internet. So we have an evolution from 1G over 2G, 3G, 4G. We are discussing 6G. 5G is widely established in most Western societies. So this is defining new capabilities to exchange information, to exchange data. The reason for that is we have the demand for more bandwidth. It's a little bit similar like the demand for parking lots in big cities like London or Paris or Munich. So there are never enough parking lots. We have never enough bandwidth. We have cloud services everywhere. We have clouds at home. We have Siri, we have Alexa, we have Azure, we have Google Cloud, Amazon Web Services, we have local clouds. In German, the department brand Lidl did start with a kind of low-cost cloud service, just as an example. So we have the demand to exchange data, and this requires bandwidth. So we have a kind of Alexa, we have a problem. And this is still ongoing because we are in the digital transformation. We are talking about Industry 4.0. The pandemic has put additional fuel onto the fire. We have IoT and industrial IoT as driving factors. So I don't expect this trend to stop. I expect it the other way around, further to increase. And this is somehow defining a nightmare for PCB designers. So I've heard quotes that some PCB designers told me, okay, we have all these differential pairs. We have fast memory interface and we have SerDes. This is a little bit like opening the box of Pandora. It's not necessarily that bad. So there's no end for the desire for more bandwidth. And to name another example, which I've mentioned already before, automotive. We have these autonomous driving. We have EVs becoming a commodity. We have advanced driving systems, ADAS. We have home automation. We have smart homes. Big cities are thinking about smart grids and smart cities, that you have automatic metering, that you don't have people coming to your home to check, okay, how much electricity or how much gas or whatever you use for getting electricity, for getting energy you've consumed. So speeds up to 56 gigabit per second are commodity these days in our customer base. So that's not exotic anymore. We have these links on board and off board. USB 4.0 is certified. We have PCI Express 6.0 certified. I did mention autonomous driving cars. They do collect a huge amount of data. So there's a study from Bosch, 3 years old, that an autonomous driving car is collecting around about half of a petabyte. A petabyte is a lot. That's the unit beyond a terabyte. Half of a petabyte of information per day on average. So we have to do something with all that data. There are dedicated SerDes links in automotive like FPD link. That's special for automotive. There's an automotive SerDes Alliance, ASR, which have all the major OEMs taking or participating in this initiative. And what's the problem? The problem is that we have a SerDes data stream, and as we would like to implement all this stuff on as little as possible board real estate, we don't have separate clock lines anymore. We have the clock embedded in the data stream. So, okay, this is not a miracle. That's a kind of engineering challenge. So the receiver has to determine where's the clock signal. It has to fetch the clock signal out of the data stream to operate in time, because the clock signal is as well paramount for the operation. So if you have that kind of data stream, this sounds trivial. Unfortunately, we don't have such a data stream. The data stream uses or is having that kind of property. And this is defining a little bit of trouble for the clock data recovery algorithm, which has to find the clock and which has to determine the data rate. So for getting an idea whether this is operational or running into a malfunction, traditional signal integrity analysis, just doing an analysis of voltage versus time of 1, 2, or 5 bits is useless. So that's not a way to tackle to address these problems. And I was quite surprised, as some of you probably know, besides just tossing software over the fence, we are doing with our application group and with my group here in Paderborn consultancy project from time to time as well. So earlier this year, we did a project supporting a customer on PCI Express links. And I was quite surprised to see similar patterns as part of the analysis we have performed. So that's a typical data stream. And the receiver side in the hardware has to pick the clock signal out of that data stream. And that's challenging. So eye diagrams. Eye diagrams, I mentioned them already, are a figure of merit for the performance of a SerDes links. So how eye diagrams are constructed. And eye diagrams are not a new technology. Eye diagrams are in place in measurement technology for more than 30 years, I would suspect. Probably even longer. I'm not a measurement expert. I'm a simulation guy. So you construct an eye diagram by doing a lot of simulations and overlaying the rising and the falling edge. And then because the switching will differ from one simulation to the next one, you have a different variation in the switching time. You have a jitter because of crosstalk. You have a jitter because of power ground noise. A lot of different jitter aspects. You have random jitter. You have determined jitter. So as more the single simulation or as more the single waveforms will differ, as more you will result in a closed eye. And you have requirements on the eye openings from the IC vendors. So they define the eye has to have a width of a factor X and has to have a height and amplitude of a factor Y. Otherwise, it is not guaranteed that the SerDes channel is operating properly. So that's a miracle, and that's the basics behind of an eye diagram. And that's a typical new kind of constraint we have if we talk about constraining and implementing SerDes links. So eye diagrams are a useful tool for qualitative analysis of SerDes links. Okay, there's always a but. That's one of the lessons I've learned more than 20 years ago. To get a proper eye diagram, you have to have a serious amount of bits contributing to the construction of that eye diagram. So we are talking about hundreds, thousands, 100,000s, or millions of bits. And depending on the simulation performance, this could take a little bit of time. So this bit error rate specification is defined in the IC vendor or in the standard specification documents. Like here, that's an excerpt from USB 2.0. This has a bit error rate target of 2 power 12. Okay, so 1 of 2 power 12 bits is allowed to be faulty. What's happening if you have more? Then the downstream device will claim I have a recognition error in the data. Please resend the data. Then the driver will resend the data. If this is failing as well, then you have a communication breakdown. So there are protocols which have even higher bit error rate requirements, like Ethernet 802.3. That has lower, 10 power 10, but we have 10 power 18 for 10 gigabit Ethernet these days. So if you assume I have to investigate the bit error rate for a USB channel, at the end, what you have to do, you have to simulate 12 million bits. Assume that you have 1 second per simulation. That's typically the performance of our time domain simulator, which is pretty fast. If you use this traditional simulation approach, 1 million bits will take around about 11 days. 10 million means 110 days. So very likely, or very obviously, this is not a feasible way to address this kind of problem. And this has been addressed by industry already a couple of years ago. The problem is, if you do not meet the bit error requirements, then you will get, more or less for sure, protocol error, because we cannot escape the physics. So you have to match the specifications defined by the silicon vendors or by the specification groups. And unfortunately, this problem is entering our traditional PCB design problem area in the very near future, because DDR5, which has been ratified last year, is using equalization, is using SerDes technology too. So we will have a growing number of design problems which have to be addressed in that way. You can derive the bit error rate directly by doing a mathematical operation, building the integral from an eye diagram. So the problem we are addressing, if we talk about SerDes design, is we try to fix a closed eye. So we would like to get an open eye. And that's what we hope to get then after validation, either using a measurement. But for the measurement, we have to have a finished prototype of the board or in a compliance simulation. So we would like to figure out what are the knobs I have to turn within the SerDes transceiver, which can be programmed, as mentioned a couple of slides ago, to open the eye if the eye is closed. Part of the modeling of such a channel are typically S parameters. I spoke about that already, because what do we have? For instance, we have cables, we have connectors. These are passive components, which are where the models provided by the device vendors are in the form of S parameters. This yields, or this points to the next problem. Experience shows that a major fraction of the S parameters has issues with passivity or causality. So you have to have a process to validate, to check the quality of S parameters. And then at the end, simulation processes most of the time are taking place in time domain. So the eye diagram we see on the right-hand side of that slide is a time domain result. An S parameter is a frequency domain piece of data. So there has to be a proper transformation from frequency domain into time domain to make S parameters usable for simulation. And that's what we offer in CR-8000 as well. So the silicon can be configured. What does that mean? That's not new either. So we know CPLEDs for more than 30 years. We know FPGAs for more than 25 years. So they became a commodity too. So we have different breeds of FPGAs, different price ranges, different complexity. They offer a huge amount of computing power for a small amount of money. They have interface to different memory technologies. So they offer DDR2, DDR3, DDR4, and the low power breeds. So that's not new. Tweaking ICs is not new. But these days, we can tweak the electrical behavior to a more extended way. So DDR memory knows on-die termination. They know digital control impedance. And for SerDes, we have now filtering technologies on driver and on receiver side. We have things called pre-de-emphasis. So that's a mechanism to tweak the signal behavior on the driver side to compensate losses. And you have filtering techniques called equalization and different equalization schemes from IC vendor A to IC vendor B on the RX side. So that's making SerDes that powerful, but as well a little bit complicated. So the PHY, which is the physical interface, can be modified by the user to address the requirements and to optimize the transmission behavior. The problem is, how do I have to set these knobs? So what are the proper settings to require the I opening, which is defined by USB 4.0 or by PCI Express or by SATA? So these modifications do include the voltage swing, the amplitude of the differential signal, the amount of energy, the schedule when different logic levels are reached, and as well techniques to restore the voltages at the receiver side. And this is typically IP, which is not disclosed by the IC vendors. So what are the PCB design constraints of a SerDes design? In detail, we have different issues to address: testability, and we have to keep in mind it is impossible to send 100% error-free data. That's not possible. The if is not the problem, or not the question. The question is how many errors do occur. The bit periods are pretty small. So depending on the data rates, we have very tiny bit periods, even faster than fast double data rate memories. As mentioned, we have the S parameters, and we have different kind of problems with bit error rates. We have intersymbol interference. We have the different jitter aspects, crosstalk jitter, power ground noise. We have the impact of the bias in the signal path of the conductor transitions. We need many bits to be simulated, and we have the smart silicon, which has been addressed by industry already a couple of years ago by introducing IBIS AMI models. And we have requirements, demands on selecting, defining the PCB technology. We have to do a thing called loss budgeting. Probably, depending on the data rate, we must be in close contact to our PCB manufacturer. Do we have proper distribution within the epoxy material of glass and resin? Or do we get a fiber weave effect as depicted by this picture? So we have a differential pair, which is seeing the two legs of a differential pair are exposed to two completely different electrical conditions. So this will change the velocity, this will change the delay, this will introduce a phase shift, and you will have a differential to mode transformation. So at the end, you may create a pretty bad EMI antenna by that situations. So layer stack definition. So that's more or less defining the basement of your design, like defining the basement of your house during the construction. Close contacts to manufacturers is pretty important for a successful SerDes design. Layer stack planning, routing layer definition, and again, these loss budgeting. And another important aspect, the power distribution system has to be designed pretty carefully, so power integrity simulation may be beneficial. Full planes are recommended, and a proper planning of the current return path. Current has to return to its source. We have different aspects for the routing of the differential pairs. Very often we have series capacitors, AC coupling capacitors in the path. So we have symmetry as a pretty important requirement. Where to do the length matching? At the end, at the source, in between, definitely not. Typically, I recommend do the length matching at the TX size, because then you have most of the differential pairs operating in phase. So you have different issues to be considered in the constraining process. you have spacing rules. You have spacing rules within the differential pair and pair-to-pair rules. So careful planning, careful constraining. If you use CR-8000, you have all the tooling in-house. The topology is rather simple. So here we have one of these SerDes technologies. It's a point-to-point with an AC coupling capacitor with termination at the end. And then you can use topologies for constraining. You can use the technology editor for defining the root width stack and the proper widths for all the impedances, for the differential impedances. Most of the constraining takes place in the constraint browser already during the schematic phase and then further refined in the layout phase. So that's the process, constraining on different levels, on ENet level, on differential pair level, on pin pair level. So that's a process to constrain the whole thing, and then you are guided during the implementation by the constraint indicators, which show you how your design is behaving against the constraints. And we have analyzing duties where we have to get an idea how is the bit error rate. We have to get an idea how is the I diagram. So IBIS models have been more or less the fuel of signal integrity simulations for more than 25 years. But IBIS models are not able to model tweakable silicon. So to address this, the industry has further evolved IBIS under the name IBIS AMI for Algorithmic Modeling Interface. That's not an idiom, that's a complete new modeling scheme. So the models are DLLs, which are executed by the simulator, and the DLLs can model TX pre-de-emphasis, and they can have the different filtering scheme at the receiver, regardless whether it's FFE, DFE, or the other different equalization schemes which have been invented by the silicon vendors. So this typically is a two-step process. You have to characterize the network, and then you perform a channel simulation, and this can be done very fast. So you can simulate up to 1 million of bits within 10 or 15 minutes. And that's quite a difference to the 11 days for 1 million bits or the 110 days for 10 million bits using traditional time domain simulations. One of the preconditions is that we have linear time invariant systems, LTI, but that's what we have if we have such a SerDes link. So that's a combination of different techniques. So it's circuit simulation combined with signal processing, and it gives you an I diagram. And that's what we would like to get. An I diagram which is reliable in a fast way. And it offers for the IC vendors the nice thing, it protects the IP, because nothing how the whole thing is operating within the chip is revealed to the end user. And we are able to simulate pretty fast, as mentioned, in a few minutes, millions of bits. So problems we do address is how the I looks like within the chip. So the I diagram in the middle, that's at the ball of a PHY, of an FPGA, of whatever, of a DSP. So that's what you can measure. And then the equalization will open the I. So that's the I diagram within the chip at the die. And here you cannot measure because you cannot plug a measurement probe within the chip. And that's where simulation can help to do a validation of the channel performance before you have built up the first prototype. That's where simulation folks raise their arm and state, here, we can help. We can help to predict the system performance. And you start within CR-8000 with the constraint browser and selecting a differential pair, which is representing the SerDes channel. I've assigned an AMI model, so we do support AMI models. They can be included in our simulation library. And then you perform this from the electrical editor, which is the entry gate, which has a special methodology to launch an AMI simulation, which opens, if you have the valid license available, a separate dialog, which you can use to parameterize the simulation, where you can define what is the bit error rate, what is this coding scheme, what is probably the amount of bits which you have to skip. So I did a project for Xilinx Kintex 7, where Xilinx is requiring the first 256,000 bits should be thrown away. And then the valid process did start. and then you run execute, because you are executing vendor IP, you are executing a DLL, and then the simulation is performed, ending up in an eye diagram and in the bathtub curve, which is the figure of merit for the bit error rate. And that's the process, of course, from 10 miles high. So it's pretty simplified, but the process is manageable. And the process is giving you reliable results. So for instance, depending on the knobs which you change, you have a different voltage swing. So please look into 0.3 volt, 1.8 volt, 0.2 volt, 1.0 volt at the TX and at the RX. So depending on the setting of one parameter, you can tweak the voltage swing of the eye diagram. And this is one example from a project we did together with the customer. It's a multi-board simulation for Fraunhofer Institute in Germany early this year. So we have 3 different boards. We have Xilinx Kintex 7 on the 2 daughter board, and we have 1 backplane. And the question was, what is the material required? Cost issue, very often. So they did compare the Rogers versus Standards FR4. You can do these material experiments within the software, which is provided with a material library, which the user can extend. And then we have the different eye diagrams. And what has been expected, the Rogers is a little bit better, but it has a cost factor of 10. So the question is, do you need it or not? That's something you have to decide then on your own requirements. This brings me to the summary and the conclusion of my presentation. So just transmitting data from A to B is not enough these days, at least not for SerDes links, because we have these eye-opening and bit error requirements. If you do not meet them, then the functionality of your channel and then the functionality of your circuit is on risk. Silicon, SerDes silicon, the PHYs, the FPGAs, the DSPs can be tuned on both ends, on driver and on receiver side. And we are suffering different noise aspects, mainly jitter, by different root causes, and they have different impacts on the eye opening. So this is creating a huge problem space. As you have to have a significant number of bits to have valid eye diagrams, new simulation techniques have been required. That's what we have implemented by having this IBIS AMI implementation. So that's allowing a fast prediction of the necessary figures of merit, bit error rate, eye opening. And that's all part of our CR-8000 solution. The whole thing is moving forward. So there are currently studies in academia to predict eye openings using artificial intelligence, machine learning techniques. But from my personal point of view, that's not necessarily science fiction, but that's pretty early. As long as we don't have that available, we have to do it in a traditional way in EDA, in PCB design. And for this, we have a very comprehensive and very powerful solution available in CR-8000. And that's what I had in mind to present. And I would be happy to answer any questions. Thank you for attending. I hope it was beneficial for you. Thank you.
Thank you, Ralf. I don't see any questions at the moment, but we still have a couple of minutes for you to ask them in the chat or the Q&A box.
Okay, seems to be pretty clear.
Yep, nothing coming through. So I'd say that's going to be it for CR-8000 today, and see you again at 3 p.m. with our partners from Quadra Solutions talking about what's new in ECADStar 2022.
Okay, thank you for me, and enjoy the further session. Again, thanks for attending. Bye for now.